There are things in the universe that do not fit, not because they are frightening, but because they refuse to settle into the explanations we have built for them. For centuries, astronomy was a discipline of slow certainty. Stars followed predictable paths. Galaxies behaved according to gravity. Light obeyed well-tested rules. The universe was vast, but it was orderly. At least, that was the assumption. Then, our instruments improved. With more sensitive telescopes, wider surveys, and new ways of observing the sky, astronomers began encountering phenomena that felt unfinished. Observations that did not complete the equations, signals that appeared once and never returned, objects that behaved unlike anything we had catalogued before. These were not ideas or speculation. They were measurements, recorded data, real events captured by real instruments. One of the earliest reminders of this came from a quiet radio telescope in the American Midwest. In the late 1970s, a large radio antenna spent its days listening to the sky, not searching for beauty, not even searching for answers, just scanning, recording, cataloging radio noise from space. Most of it was unremarkable. Cosmic static, the background murmur of the universe. Then, for just over a minute, something cut through that noise. A signal appeared, sharply defined and unusually strong. It arrived from a narrow region of the sky and occupied a very specific frequency, one closely tied to hydrogen, the most abundant element in the cosmos. The signal rose above the background, held steady, and then vanished. It never returned. What made it unsettling was not just its strength, but its precision. Natural cosmic sources tend to be messy, spread across ranges of frequencies. This signal was narrow, focused, and brief, as if it had been intentionally confined. Astronomers searched for it again and again. They pointed larger, more sensitive instruments at the same region of space. Nothing. The sky remained silent. Decades later, the signal remains unexplained. It could have been a natural phenomenon we do not yet understand. It could have been interference that escaped detection. Or it could have been something else entirely. Science does not choose answers based on comfort. When evidence is insufficient, uncertainty remains. And that uncertainty became a pattern. As observation expanded beyond radio waves into optical surveys, infrared measurements, and long-term stellar monitoring, other anomalies began to appear. Not signals, but stars themselves. Objects once thought to be among the most stable structures in the universe. Some stars dimmed dramatically, then recovered, without rhythm or repetition. The scale of the dimming exceeded what planets could cause. Dust explained part of the behavior, but not all of it. The physics worked, until it didn't. Elsewhere, astronomers mapping the radio sky encountered shapes they had never seen before. Enormous circular structures, visible only at radio wavelengths, surrounding ordinary-looking galaxies. Perfectly curved, vast beyond scale, with no clear mechanism to explain their formation. At even larger scales, patterns emerged that challenged foundational assumptions. Structures of galaxies stretching across billions of light-years, larger than theory predicted should exist. Regions of space so empty they strained the limits of cosmic structure formation. And beneath it all, embedded in the oldest light we can see, subtle irregularities appeared, cold regions in the afterglow of the Big Bang that resisted simple explanation. None of these discoveries overturned physics on their own, but together they told a quieter story, that the universe is not finished revealing itself. Every time we believed we had mapped the boundaries of understanding, something appeared just beyond them. Not to mock us, but to remind us that knowledge expands unevenly, that certainty is always temporary. Astronomy does not advance by finding what we expect. It advances by confronting what we don't. And as the catalog of strange observations continues to grow, one truth becomes harder to ignore. The universe is not obligated to fit our models, and we are still very early in learning how it actually works. The next clues did not arrive as whispers from radio antennas, but as distortions in starlight itself. For most of modern astronomy, stars were considered reliable. They aged slowly, changed predictably, and followed patterns that could be modeled with remarkable precision. When a star dimmed, there was usually a clear reason. A planet passed in front of it. A cloud of dust intervened. The explanation was rarely mysterious. Then astronomers began watching thousands of stars continuously, without interruption. Instead of brief snapshots, they collected years of uninterrupted data. And within those long, unbroken records, patterns emerged that had never been visible before. Some stars dimmed far more than planets could account for. Not by fractions of a percent, but by tens of percent. The drops were irregular. They had no consistent timing, no repeating rhythm, no obvious orbital signature. The star would fade dramatically, then recover, then remain stable for months or years before dimming again. The problem was not the observation. The data was clean. Multiple telescopes confirmed it. Different instruments, different wavelengths, same result. Something was blocking enormous amounts of starlight. But whatever it was, did not behave like anything familiar. Planets were too small. Dust clouds should have changed the color of the star's light, but in some cases the color barely shifted. Catastrophic collisions should have left thermal signatures, glowing debris detectable in infrared light. Often, none appeared. The models worked until they didn't. And once again, astronomers were forced into an uncomfortable position. Not because an exotic explanation was appealing, but because ordinary explanations were insufficient. Science does not begin with extraordinary claims. It begins with failed expectations. While stars puzzled observers on relatively small scales, radio telescopes were uncovering something even harder to reconcile. Structures so vast, they challenged intuition entirely. In radio surveys of distant galaxies, astronomers began noticing immense circular patterns. Perfect or near-perfect rings of radio emission, floating in space like outlines without interiors. They were not artifacts. They appeared consistently across instruments and observing runs. Each ring was enormous. Some spanned hundreds of thousands, even millions of light years. At their centers sat galaxies that appeared otherwise unremarkable. No violent jets, no obvious explosions, no signatures that could easily explain such colossal shells. Supernova remnants were far too small. Planetary nebulae were confined to individual stars. Known galactic outflows did not match the geometry or scale. The circles existed, but their origin did not. At still larger scales, the universe began to look less uniform than theory suggested it should. Galaxy surveys revealed immense arrangements, arcs, rings, and filaments stretching across billions of light years. Structures so large that, according to standard cosmology, they should never have had time to form. Gravity simply should not have been able to assemble matter on those scales within the age of the universe. Yet there they were. Some researchers questioned whether these patterns were real or statistical illusions. Human brains are excellent at seeing order in randomness, but repeated analysis reduced the likelihood of coincidence. The structures persisted under scrutiny. If they were real, something about our assumptions was incomplete. At the opposite extreme of density, astronomers mapped regions of space that seemed almost empty. Vast cosmic voids, where thousands of galaxies should have existed, but didn't. These voids were not unusual in principle. The universe forms a web of filaments surrounding empty regions, but some voids pushed theoretical limits. They were almost too empty, too large, expected. Not dramatically colder, but cold enough to stand out against a background that is otherwise astonishingly uniform. The probability of such a feature appearing by chance was low. Not impossible, but uncomfortable. Attempts to explain it invoked enormous voids, subtle relativistic effects, or the statistical quirks of a single observable universe. None were fully satisfying. And still, the anomalies continued. Stars containing radioactive elements that should have decayed long ago. Objects entering the solar system from interstellar space with shapes and motions unlike anything previously observed. Explosions brighter and faster than known stellar deaths, appearing suddenly and vanishing almost as quickly. Each discovery alone could be dismissed as an oddity. Together, they formed a pattern. Not a pattern of answers, but a pattern of questions. A growing realization that the universe is not misbehaving. It is behaving exactly as it does. Our understanding is what remains incomplete. What links these discoveries is not their subject matter, but their effect. Each one exposes a boundary, a point where prediction stops working cleanly, a place where models still function, but only partially, accurate in some aspects, inadequate in others. This is not failure. This is how progress announces itself. Science does not collapse when it encounters contradiction. It sharpens. For most of history, the universe appeared simpler than it truly was, not because it lacked complexity, but because our tools were blunt. We observed only what was loud, bright, or close. The quieter, subtler phenomena remained invisible. As instruments improved, the universe did not change. Our access to it did. And what we found was not chaos, but layers. Signals that appear once and never again are not evidence of disorder. They are evidence of rarity. Stars that dim unpredictably are not broken stars. They are telling us that stellar environments are more dynamic than our simplified categories allow. Structures that exceed theoretical size limits are not violations of physics. They are invitations to re-examine how those limits were derived. History is filled with moments like this. At the end of the 19th century, physics was considered nearly complete. Classical mechanics explained motion. Electromagnetism unified electricity and magnetism. There were only a few small problems left to resolve. Then measurements began to disagree. Light refused to behave as expected. Time and space stopped acting independently. Gravity failed under extreme conditions. None of these contradictions destroyed physics. They transformed it. Relativity and quantum mechanics emerged not because scientists were bored, but because reality demanded new descriptions. The same process is unfolding now, quietly, across the cosmos. Consider the scale of what we are attempting. We are building models meant to describe everything from subatomic particles to structures billions of light-years wide, all within a single coherent framework. That such a framework works as well as it does is remarkable. That it occasionally falters is inevitable. The universe is not obligated to be simple. Many of the strangest discoveries of the past few decades share a common trait. They were not found while searching for them. They appeared as side effects, unintended revelations uncovered while instruments were aimed at something else entirely. Radio telescopes built to map the sky found signals that defied classification. Space telescopes designed to search for planets uncovered stars that behaved in unprecedented ways. Surveys meant to measure large-scale structure revealed patterns that strained theoretical assumptions. This is not coincidence. It is methodology. When observation becomes broad and unbiased, the unexpected surfaces. And with each anomaly, scientists face a choice. Dismiss it as error, or treat it as information. The history of science strongly favors the second approach. Errors disappear with better data. real anomalies persist. Persistence is the key distinction. The unexplained phenomena that endure across instruments, methods, and years are the ones that matter. They are the pressure points where understanding is incomplete. They do not announce revolutions loudly. They accumulate quietly, waiting for someone to connect them in a new way. Not all mysteries will share a single explanation. Some will resolve into mundane processes once data improves. Others will require refinements to existing theory. A few may point toward genuinely new physics, and some may remain unresolved indefinitely. That uncertainty is not a weakness. It is a feature of honest inquiry. To study the universe seriously is to accept that many answers arrive slowly, and some not at all. Data can be precise while interpretation remains uncertain. Models can be predictive while still incomplete. What matters is not that we lack explanations, but that we recognize where they fail. Because it is at those edges, where prediction breaks down and observation persists, that the universe teaches us the most. When viewed together, these unresolved observations begin to change the way scale itself feels. Not physical scale, but conceptual scale. The distance between what we think we understand and what reality continues to show us. It is tempting to imagine scientific knowledge as a structure nearing completion, as if, with enough data, the remaining gaps will eventually close and the universe will resolve into something tidy. But history suggests the opposite. Each time understanding deepens, the horizon expands. New questions appear where answers once seemed sufficient. The universe does not grow simpler as we learn more about it. It grows richer. Consider how young this process truly is. Modern astronomy began only a few centuries ago. For most of human existence, the stars were fixed points on a dome. No distances, no physics, no sense of scale. In just a few generations, we moved from that view to mapping billions of galaxies, measuring the age of the universe, detecting ripples in space-time itself. And still, the cosmos remains filled with things we cannot yet explain. This should not be surprising. We are attempting to understand a universe nearly 14 billion years old using tools developed within a fraction of that time. Our models are sophisticated, but they are provisional. They work where tested, and they fail where reality extends beyond those tests. What is remarkable is not that anomalies exist. It is that we can recognize them at all. To identify something as strange, you must first understand what normal looks like. The fact that astronomers can say a structure is too large, a signal too narrow, a star too old, or a void too empty means that our baseline knowledge is already extraordinarily precise. Strangeness is a sign of progress. Every unexplained phenomenon marks a location where observation has outrun interpretation, where data arrived before understanding was ready to receive it. This is not a crisis. It is the natural state of exploration. There is also a deeper implication hidden in these discoveries. They remind us that the universe is not centered on human expectations. It does not arrange itself to be easily understood. It does not repeat phenomena for convenience. Some events happen once. Some processes operate on timescales far longer than civilizations. Some structures emerge from conditions we may never be able to recreate or observe directly. And yet, within this vast and indifferent system, something improbable exists: observers. From a small planet orbiting an ordinary star, we have learned to detect signals across cosmic distances, to infer the behavior of matter billions of years in the past, to notice when reality deviates, even slightly, from prediction. The mysteries themselves are evidence of this achievement. If we truly understood nothing, nothing would appear strange. Everything would simply be unknown. Confusion would be uniform. Instead, confusion is localized, appearing only at the edges of knowledge. where understanding is strong enough to notice its own limits. That is where we stand now, at the edge of explanation, surrounded not by ignorance, but by questions shaped by insight. The universe continues to reveal itself unevenly. Some regions are mapped in exquisite detail. Others remain shadows, hinted at only through anomalies and indirect evidence. Each unexplained signal, structure, or star is not a failure of science, but a marker pointing forward, toward better instruments, better theories, better questions, and perhaps toward discoveries that will once again redefine what we think the universe is. There is a quiet consequence to all of this that often goes unspoken. When the universe refuses to fully explain itself, it changes how we understand our place within it. Not by diminishing us, but by reframing us. For much of history, meaning was tied to certainty. To know was to be secure. To have answers was to feel grounded. But the cosmos does not reward certainty in that way. It rewards curiosity. It advances not through confidence, but through patience with the unknown. The strange discoveries scattered across modern astronomy are reminders of that discipline. They tell us that reality is deeper than our descriptions of it, that even the most successful models are approximation. That knowledge is not a destination, but a moving boundary. And this has implications beyond science. To live in a universe that is unfinished, at least from the perspective of understanding, is to accept a particular kind of humility. Not the humility of insignificance, but the humility of participation. We are not outside the universe looking in. We are inside it, shaped by the same laws we are trying to uncover. The atoms in our bodies obey the same physics as distant stars. The forces that sculpt galaxies also govern the structure of matter in our cells. When we study the universe, we are not examining something foreign. We are studying the context that made us possible. The mysteries matter because they remind us that existence is not static. Stars behave in ways we did not anticipate. Space contains structures we did not predict. Time preserves signals that appear once and never again. And in each case, the universe is not being deceptive. It is being honest, revealing itself only as far as our tools and ideas allow. There is something profoundly human in that exchange. We build instruments. The universe responds with data. We interpret. It surprises us. And then we build better instruments. This cycle has repeated for centuries, each time expanding the sphere of what we can ask. Not what we can answer, but what we can meaningfully question. The unanswered questions are not failures left behind by progress. They are its engine. They motivate new telescopes, new methods, new generations of thinking. They ensure that understanding never becomes complacent. That wonder does not fade into routine. In this sense, the universe's strangeness is not an obstacle to meaning. It is its source. A fully understood universe will be predictable, static, closed. It would leave no room for discovery, no space for awe. Instead, we inhabit a cosmos that continues to resist completion, a universe that remains open to revision, reinterpretation, and surprise. And within that openness, something remarkable happens. A species emerges that notices, that looks at a signal lasting less than 2 minutes and thinks about it for decades. That observes a star dimming and refuses to accept a convenient answer. That measures the faintest fluctuations in ancient light and asks what came before. That insistence on understanding rather than settling is rare. As far as we know, it exists here, not because Earth is large, not because it is central, but because it is conscious. In a universe filled with matter, energy, and vast stretches of emptiness, awareness is the anomaly. And like all anomalies, it demands attention. The strange things we find in space do not make the universe feel colder or more distant. They make it more alive, more dynamic, more unfinished. They remind us that we are not late to understanding the cosmos. We are early, and that means the story is still being written. We are living inside a moment that future histories of science will likely describe as transitional. Not because we have reached the limits of knowledge, but because we have become acutely aware of how far those limits still extend. The strange signals, the dimming stars, the impossible structures, the empty voids, the ancient light that refuses to smooth itself into expectation. All of them are reminders that the universe is not a solved problem. It is not a closed book waiting to be summarized. It is an ongoing process, unfolding across scales and times far beyond human experience. And yet, here we are, on a small planet, orbiting an unremarkable star, inside one galaxy among trillions, capable of detecting when something does not make sense. That alone is extraordinary. Most of the universe is silent. Most of it does not observe itself. It follows its laws without reflection. But in at least one place, matter has arranged itself into a form that asks questions, that notices patterns, that recognizes anomalies, that feels compelled to understand. When a signal appears once and vanishes, it is recorded. When a star behaves strangely, it is monitored for years. When a theory fails, it is revised rather than protected. This is not the behavior of a species that has finished learning. It is the behavior of one that has just begun to realize how much remains unknown. The universe does not owe us clarity. It does not promise answers on human timescales. Some mysteries may persist longer than civilizations. Some may dissolve quietly as better data arrives. Others may trigger shifts in understanding as profound as those that reshaped physics in the past. We cannot know which will be which. What we can know is this: confusion is not the opposite of knowledge. It is a stage within it. Every anomaly marks a place where curiosity is alive, where understanding has reached far enough to recognize its own edges, where the universe has revealed just enough to provoke deeper questions. That is not a failure of science. It is its signature. The cosmos remains vast, indifferent, and largely empty, but it is also generous in one crucial way. It allows itself to be studied. It leaves traces, signals, patterns, imprints in light and matter that persist long enough for minds like ours to notice. And we respond. We build instruments. We refine theories. We argue, revise, and try again. Not because we expect certainty, but because the act of understanding is itself meaningful. The strange things we have discovered in space are not warnings. They are invitations. Invitations to keep looking, to keep questioning, to accept that reality is richer than our current explanations. They remind us that we are participants in an unfinished story, a universe still revealing itself, a science still evolving, and a moment in cosmic history where awareness has begun to look outward and wonder. The mysteries remain, and that is exactly how progress begins.